Hi everyone, this is the master thesis defense for Ryan Miller. He's our master student and previous are our undergraduate students here, and he could finish his master in 3 semesters. So his thesis topic is about the resilience assessment of active distribution network, and I will give the floor to Ryan to present his work.
Thank you, Miriam. Good afternoon, everybody. As Miriam said, my name is Ryan Miller.
And can you unmute yourself and I can mute
All right. So thank you for joining me as I present my thesis defense today. So on resilience assessments of active distribution networks. So getting into this, first of all, I want to talk about the definition of resilience. Generally speaking, this is defined as the ability of a system to recover from disturbance. The way in which this pertains to power systems and the specifics of how to apply this is still a topic of considerable debate, considering the interest in resilience has only really come about in the last couple of decades, So the difference between resilience and reliability is such that reliability is how the power system has been designed historically. It's meant to be reliable, and the study of reliability has a clearly defined definition and well-developed metrics that define what reliability is, versus resilience, which, because it's such a new field of study, the definition across the entire industry has not been standardized significantly, and the metrics used for portraying how resilient a system is to extreme events has not been developed extremely well. So as I go through my presentation here, keep in mind this image here, which is a profile of an extreme event going from before the extreme event occurs, where the system operates at a healthy performance level, where after extreme event occurs, the system degrades down to a degraded performance before recovering over time back to healthy performance after resources available to the recovery process have been assessed and a strategy has been developed. The motivations behind this research are mostly based on the increased frequency and severity of extreme events that have occurred in recent years. Main ones that come to mind, as I'm sure we all remember, are the polar vortex, which caused extreme load curtailment in this past winter over in Texas, wildfires in California that have happened almost annually for the past 5 years, as well as hurricanes across the eastern US that occur almost annually as well. The research gap this is trying to fill is developing a probabilistic approach to extreme event system degradation, where many works otherwise assume that a level of system degradation has occurred before evaluating a system's recovery and the performance during that recovery. Also trying to develop a generalization of equipment impact technologies for any extreme event. Other works tend to perform single, highly focused event simulations or analysis on only a single type of component during an extreme event and the recovery process, versus this, which is trying to generalize the impact of various types of equipment to an arbitrary extreme event. And third of all, defining clear metrics for an arbitrary system for evaluating a power system's resilience in its recovery process, both immediately following and until the entire system recovers from an extreme event. The objectives here are developing a simulation technique for active distribution networks, the extreme event impacts, and the system recovery, with a proposed resilience metric being discussed here and using those metrics for evaluating the system recovery. So the first part in this process was developing a regional geography for which a power system, which is specified in the paper, could be overlaid onto and laid out to have an extreme event occur on it. The process in which this is done is using a map of random values, which are then blurred using a Gaussian algorithm until a relatively smooth terrain has been developed. The benefits of this are it's, first of all, an arbitrary system an arbitrary geography that incorporates high and low areas of elevation, but this system could be extended to standard geographic information survey maps that provide topography if you're looking at more of a real system that was actually laid out on a terrain. For extreme event simulation, the process by which these events are simulated takes three parameters, those being the event type, the local severity for that event, and the regional topography, which was just discussed. And the output is an impact severity map, which has values that range between 0 and 1 in a normalized fashion to represent the probability of an extreme event impacting that region. The event type could be anything from like a hurricane or a tornado to a flood or a windstorm, etc. Some sort of regional disaster that could impact a topography. The local severity parameter is a value between 0 and 10 as an integer, which represents an aspect in terms of the local terrain of how severe that event is. And several examples of that will be discussed here in the following slides. And the regional topography, again, what was just described, could be a real topography or an arbitrary one, which is the case for this simulation. The four types of extreme events which were modeled in this work are floods, tornadoes, windstorms, and wildfires. The flood is going to be the event that's focused on primarily when portraying the results here, considering the impact region for a flood is much more significant, and you'll see that in the following slides as well. So for a flood, in determining how severity generates a impact probability map, the severity parameter from 0 to 10 defines how high the water level for that flood rises in relation to the elevation profile of the region. So a severity 0 would mean there's no water coverage in the region. A severity 10 would mean that the water covers all of the land in the region. That water level then goes into an impact generation function, which uses a logistic function for smoothing and additional aspects here. But it takes the height of the topography and the water level and evaluates that in the logistic function in order to approximate what could be additional impacts above the level of the water level. So think soil destabilization for equipment foundations or weakening of the terrain because of how high the water level reaches during the event. As a side note here, throughout all of these impact maps that you see, yellow regions are areas of high impact probability. Purple or blue areas are regions of low impact probability. So that'll be true across all of these. For a tornado, it's based on the assumption that tornadoes tend to move uphill and also includes a random acceleration aspect to it, such that at every time step in the simulation, a Gaussian weight matrix, which has a sum of all values, which goes to 1, is centered at a tornado's location, and the width and height of that Gaussian matrix is based on the severity of that tornado event. But for each time step, the tornado is moved according to an acceleration that is based on the terrain as well as random noise. And at each time step, that weight matrix is additively modified to the impact probabilities map to assess the impact probability along the path of that tornado. So the longer tornado stays in one place, the brighter the impact probability will be. The faster it moves across a specific area, the lower that impact probability will be. For a windstorm, the simulation is based on a ray tracing method, where a random vector along 360 degrees is determined for the source of the wind, and straight lines are traced across the topography, evaluating where each of those points along the line increase in height and decrease in height. So for every increase in height, a 2% impact probability of the elevation change is assessed. For every decrease in elevation, a 1% decrease in impact probability is assessed. And if the terrain stays flat, 0.5% decay of impact probability from that point beyond. The idea being that wind is more damaging on the windward side of hills versus the leeward side of hills. And so, as you can see from the impact map here, the for a wind vector coming in this fashion at a hill sitting here, you'll have a streak of impact probability trailing off of the hilltop until the simulation concludes. Finally, wildfire. This was the most complex of the simulated extreme events. The severity parameter here dictates the number of initial fires, the lifetime of each fire, the probabilities of uphill, downhill, and indirect spread of this fire, the maximum number of fires to allow for reasonable simulation performance, and the radius of indirect fire spread. And the assumptions made during this were that fire spreads uphill easier than it spreads downhill, and that fire can spread indirectly via embers that are flying through the air. An example of the wildfire impact can be seen here, where the brightest point in this web-looking albatross in the middle of the image is where the fire originates from, and the fire spreads outward in a more or less random pattern that's also determined by the terrain of that region. So finally, getting into modeling the test system, the system that's used here is based on one of the resources, which is a test system specification. This test system specifies a 4-microgrid, multi-microgrid system in which each of the microgrids can be islanded from one another and operated adequately, or can be connected between each of the microgrids for a peer support mode, or otherwise connected to the bulk power grid in a grid-connected mode. Each of these microgrids includes distributed energy resources in the form of battery energy storage systems, photovoltaic systems, wind turbines, and synchronous generators. This is a one-line diagram that's specified in the test system paper, and it lays out each of the locations of the distributed energy resources, and also shows which buses within each microgrid are connected between each of the microgrids and to the utility grid. Overall, this system includes 41 buses, 52 lines, 15 PVs, 4 wind turbines, and 4 synchronous generators, where those synchronous generators can be used to support each of the individual microgrids they're connected to without the help of any other energy resource on that grid. The peak load for this entire system is 30.8 megawatts. For each of the equipment connected to the buses, these are the connection diagrams for how that is modeled. The original paper dictates having transformers where each of the switches are in this schematic here. However, due to simplicity of modeling, transformers were replaced with simple switches, so you can either define the loads on those buses or the equipment on those buses as connected or disconnected. And laying out the one-line diagram, which was shown previously in a geographic fashion, relative to the utility grid, which is placed at the origin in this image. This is the map that's produced. Within this map, each of the microgrids is highlighted for its area of responsibility, just to identify which buses belong to which microgrid a little bit easier. In order to overlay this onto the regional topography, it's just a matter of scaling and translating this according to the size of topography which is requested. And for this project, the scale is a 1-to-1 ratio, so a 1 coordinate change represents a 1 meter change in physical dimensions. So now that we have a system and we have extreme events, the system degradation per the extreme events can be calculated. This is done using the equipment reliability, which takes into account the equipment's time in service, the equipment's location, X and Y on the regional topography, the equipment type that's in question, whether it's a bus, an overhead line, an underground line, load, synchronous generator, etc. And it also uses the impact probability of failure given the type of equipment according to the type of extreme event that's simulated. So for buses, the buses are lines, overhead lines. The damage that those will incur is directly related to how high the water level is in relation to the conductors that sit above the water surface, and whether it might be impacted or contacted by debris or other aspects such as that. Finally, the impact probability map generated by the extreme event simulation comes into play here by looking at the individual coordinate X and Y and the probability of impact from 0 to 1 taken from that map. Calculation of the probability of damage given XY coordinate and equipment type is shown in this equation here. And the value of that probability of damage is then compared with a random value via Monte Carlo simulation to evaluate what the system degradation is for a single simulation run. This is an example of the most likely system degradation according to a level 5 severity flood. And within this map, the green equipment represents equipment that's operating normally. Red equipment is that which has failed, and black equipment is disconnected from some other equipment due to failure or otherwise identification of that equipment should be out of service. For the purpose of the simulation, equipment is only disconnected if a piece of equipment that it connects to is otherwise failed. So all equipment should normally be operating normally. And as you'd expect, areas of high impact probability have failed equipment much more than, well, as you'd expect from the impact of the extreme event. In order to perform the recovery simulation, this is the general steps that are performed. So first of all, the system is loaded in from the configuration specified in the test system specification. The simulation is built according to user-defined configuration parameters such as the extreme event type, extreme event severity, repair strategy, number of repair crews available, and energy storage management strategy. After impacting the system and degrading the equipment, recovery operations can be performed, which log the simulation results and save the output for calculating resilience metrics after the simulation. The loop of the recovery itself goes through these stages. First of all, it calculates what islands exist within this power system, and then looking at available generation resources and required loads that exist in those islands to calculate the curtailment of loads within those islands. If the island includes energy storage systems, the energy storage system availability, so the amount of power it can supply to the grid, to that island, is determined at this stage as well, where the battery will attempt to provide as much power as it can if it has the charge available for that. And there's a shortage of generation relative to load on that island. After incrementing the simulation time, then all equipment that's normally operating and is in service has a chance of failing with an in-service failure due to its own reliability and time in service. That'll be discussed on the next slide here. The energy storage system state of charge is then updated to reflect how much it was set to charge or discharge at the rate at which it was charging or discharging according to the curtailment strategy. And then work crews who are already repairing equipment are told to work for 1 hour, and those who complete those tasks within that time frame are then assigned new tasks for repairing new equipment after that. So for in-service failures, the probability distribution for in-service failures is based on a highly skewed model distribution, where reliability thresholds of 70%, 80%, and 90% have the given probabilities of impact shown in the table on the right. The idea here being that for each time step in the simulation, a piece of equipment has these probabilities of failure, which would extend the repair time for the simulation. Introduction of randomness into the recovery simulation, which is part of the reason that Monte Carlo simulation is required for analyzing the results here. There are 3 aspects which remain constant across any simulation. Those are the regional topography, which is generated, the extreme event impact probability map, and the equipment initial operating times. Beyond that, aspects such as repair crew skill, energy storage, state of charge initially before the extreme event occurred, system degradation threshold, and initial hour of the yearly event concludes and recovery begins, as well as random in-service failures during recovery, all are random. Additionally, one final aspect here for the simulations is the selection of repair priorities. And in the simulations discussed here, this process is a blind pick where equipment is just chosen randomly without any any particular strategy of trying to repair specific buses or restore loads or anything along those lines. And so this is an additional aspect of randomness that comes in. The resilience metrics proposed here are, I have 7, and several of these can be split to analyze critical loads versus all loads, and I'll mention those here. But first of all is system recovery time, which is simply the amount of time it takes from when the extreme event occurs until all equipment is repaired and back to normal operating state. Second piece is equipment impact percentage, which takes the ratio of number of impacted pieces of equipment to total number of equipment in the system. Equipment degradation recovery rate is the ratio of equipment impact percentage to system recovery time, and this evaluates a percentage per hour that a system is expected to recover at. This is going to be based heavily on the amount of resources available to a recovery process. Energy not supplied, this can be split up for critical and non-critical, and this represents the total amount of energy throughout the entire recovery process, which is not delivered to loads. So integrating the amount of power not delivered over the entire recovery duration. Average power not supplied then takes that energy not supplied and divides it by the system recovery time to give you what the average power not delivered to the system loads are. Again, this can be divided to critical versus all loads. Energy supplied ratio gives a ratio of how much energy was delivered to equipment versus the amount of energy requested, amount of energy delivered to loads versus energy requested by loads. Again, critical versus all equipment here. And average system service availability index, which is based off of the reliability index of a similar name. And this looks at the number of customers receiving power versus total number of customers across the entire system and throughout the entire recovery time, averaged. So simulation results here. As I mentioned a couple times before, the simulations were performed using Monte Carlo, and the states of each piece of equipment is logged for every hour of the recovery process. Those equipment states are then used to calculate the resilience metrics, which were just discussed. And for all of the simulations performed through Monte Carlo, a histogram plot of each of those values is displayed to identify what trends exist throughout the random simulation process. And because of the shape of the results process here, and I'll show you an example in the next slide, the median value of these results is chosen due to outlier values, which pull the mean value for the metrics off of the most likely recovery times or indices. So as an example of some of these reliability results here, system recovery time for a single repair crew, blind pick repair strategy, preferential full energy storage system management strategy, and level 5 flood is shown here at the right. As you can see, the number of outlier recovery times that exist for this configuration skews very high into the thousands of repair hours, and therefore the green line that you can see on this plot, which lies right on the most likely repair time region. That's what's taken as the measure of central tendency for the metric. So in addition to individual metrics, a trend analysis was performed here based on varying the number of repair crews that can concurrently repair equipment throughout the recovery process. This is done by holding all other configuration parameters constant and just varying that one aspect. And these trends aren't unexpected by any means, because as you'd expect, with more resources available for repairing a system, the resilience metric each individual resilience metric should improve to its nominal value. So system recovery time shown on the left here is, as you'd expect, decreasing, but this doesn't decrease to 0. It decreases asymptotically to the longest repair time of any piece of equipment in the system. The average power not supplied, as you'd expect, with faster recovery time and more resources put toward recovery, the power not supplied will decrease. The energy supplied ratio, again, as you'd expect, increases as you get more resources online and more loads reconnected to be supplied with energy, with power. And then the average system service availability index, again, increases as the number of loads reconnected in a more rapid fashion increases and the number of customers supplied by those loads increases. So these trends are not unexpected by any means. So the conclusion of this work here, the primary objectives for this work have been adequately completed. A model and simulation of an active distribution network has been produced. Simulations of extreme event impacts and probabilities of impact have been performed. Resilience metrics have been proposed, and those resilience metrics have been used to evaluate simulated system recoveries for a wide range of random aspects that occur within those simulations. And additionally, a trend for modifying a single parameter of the recovery process has been analyzed. Future works that can spur off of this include incorporating power flow analysis into the recovery simulation, where you look at possible overloading of lines where the line is undersized for delivering the amount of power requested. Evaluating additional resilience metrics, perhaps based on an economic analysis of the incremental change in a specific metric's value versus the cost increase for achieving that increased resilience. A strategy optimization could be performed here as well, where you look at what the best battery energy management strategy is, that you continue to supply perhaps critical loads instead of trying to maximize the number of loads that are supplied, or otherwise improving the repair prioritization strategy, where if you have perhaps a single piece of equipment that's failed between two islands and you want to reconnect islands fast, or if your priority is recovering generation, or priority is reconnecting loads, those different repair strategies could be evaluated for increases in resilience metrics. Economics of supplying loads, so economic dispatch of energy, could be evaluated as well if that information was available, or otherwise generalizing this system, this simulation process, or any arbitrary system specification passed into it, using a automatic geographic bus layout generator could also be performed. But those are works for a future iteration of this work. So that concludes my presentation here, and I'll accept any questions that anybody might have at this point.
Do we have anyone online?
Pass this back to you.
Okay. Yes, we have just set with the. Okay. Just one.
Questions from our online attendees or in person?
Good.
So when you chose the layout, did things like putting did you pick one topology for the layout then that you had, or did you use multiple topologies? So like I guess my thought is like windmills tend to perhaps perform better higher up. Was that type of thing considered in your simulations?
It wasn't. The layout was strictly taken to the layout of the buses on the geography was strictly taken to make sure the buses fit within the generated region. Any incorporation of elevation profile of the terrain with where the buses are placed was not taken into account.
Was there a specific one that a specific event that was the first?
The flood was the primary one, which was evaluated with simulation results here. Mostly because when I started this process, I was working in MATLAB, And later on, because of the fact that I dislike MATLAB for doing any larger simulation, I switched this into Python, and so the only one of those events that I was able to merge in a timely fashion was a flood.
Questions? Ron, Neda? Good.
Well, thank you for coming in.
Yeah, thank you.